And now we come to the topic of force and motion. In this video, we take a look at Newton's laws of motion. Force is basically a push or pull influence that can change the state of motion of an object. For now, when we say state of motion of the object, we mean the velocity of the object. We know from common experience that whenever we push or pull something, not only can we change the position of the object, we can also change the velocity of the object. And that's the basic definition of what a force is. It's an influence that can change the state of motion of an object. When we push or pull something, we always do so in a particular direction. Which means force is a vector quantity. And as such, when you do force analysis, you have to use your vector analysis because force is a vector quantity. For instance, when you add forces together, you have to use your component method to get the sum of the forces, or what is called the net force. When you have an object and you have several forces acting on the object will behave according to the net force, the summation of the forces acting on the object. F net is equal to the sum of all the forces acting on the object, so it's equal to F1 plus F2 plus F3 and so on. Unit of force is Newton, capital N. 1 Newton is equivalent to 1 kilogram meter per second squared. This is an MKS system unit. For the CGS, we also have the unit for force, dyne. 1 dyne is equivalent to 1 gram centimeter per second squared. So be able to convert from Newton to dyne to Newton. 2 units for force. 1 Newton, MKS, 1 dyne, CGS. Again, be sure to use your component method when adding forces together because force is a vector quantity. Newton gave us 3 laws of motion relating force to the motion of an object. Newton's first law of motion tells us if no net force acts on a body, the body's velocity cannot change. Meaning, if you sum up all the forces acting on the object and F net is equal to 0, then the velocity of the object cannot change. The velocity of the object is constant. So if F net is equal to 0, the velocity is constant. This implies that the reverse is also true. If F net is not equal to 0, that means the velocity can change. The velocity of the object is not constant. And we learned from our kinematics, from our discussion of motion along a straight line, that if the velocity of the object is constant, rate of change of velocity is zero. But if the velocity is not constant, then rate of change of velocity is not equal to 0. Rate of change of velocity is acceleration. That means F net is related to the acceleration of the object. That is to say, if F net is equal to 0, the velocity is constant. That means the acceleration is 0. And if F net is not equal to 0, velocity is not constant. That means the acceleration is not equal to 0. Thus, the acceleration experienced by the object depends upon the net force acting on the object. If the first law of motion implies the relationship between net force and acceleration of the object, the second law of motion, Newton's second law of motion, gives us the relationship between the two quantities, between the net force acting on the object and the resulting acceleration of the object. For constant mass, so let m be constant, the net force acting on the object is just equal to mass of the object times acceleration of the object. F net is equal to ma. And lastly, we have Newton's third law of motion. Some books refer to this as the law of action and reaction. When we say action, we're talking about force, particularly, say, applied force. And when we say reaction, that's also a force. For every action, there is an equal but opposite reaction. When you have one object pulling a second object, so F action is applied on the object by object 1. The object will react by applying a force on the first object, F reaction, in the opposite direction. So if a horse is tied to a cart, the horse pulls the cart, so F action is applied on the cart. The cart will react by applying force on the horse, F react. If you compare F action and F reaction, they are equal in magnitude but opposite in direction. F reaction is equal to negative F action. Again, F action, a force applied by the horse on the cart. F reaction is reaction force applied by the cart on the horse. Third law of motion. Note that F reaction is equal to negative F action. They will not cancel out, however. For instance, you say you order the horse to pull the cart to move forward. Say the horse refuses, telling you that since if it applies 5 newtons on the cart will react and apply 5 newtons on it, canceling out its F action. Therefore, it doesn't make any sense for the horse to pull the cart. That's a common misconception of the third law of motion. They will not cancel out even though they are equal but opposite in direction. They will not cancel out because they are applied on two different objects. F action, for instance, with respect to this figure, F action is applied on the cart, while F reaction is applied on the horse. For forces to cancel out, they must be applied on the same object or on the same point. F action and F reaction are applied on different objects, therefore they will not cancel out. That's it for now. We'll continue our discussion on force and motion in the next video, wherein we look at the types of forces that you are likely to encounter in your study of basic physics. So thank you for watching.